are just linked in the those are just linked inside of the notebook as kind of a reference. So you can kind of read through those if you want as well. Yeah, so I'll go ahead. Oops. Okay, so we have, I'll start with this one. Okay, cool. So today we're going to be focusing on TensorFlow with keras. Basics, keras is an open source library that provides a Python interface for neural network development. Keras 3 is out now, which is kind of, time flies. It runs on top of JAX, TensorFlow, or PyTorch. So these are all different backends. You can choose to run keras on top of any of these and have a much more high level interface. And that's good because it can speed up development. So they make it very simple to develop basic models and just kind of prototype things easily. Um, it has a really flexible interface, so a lot of the workflows follow a similar path, whether or not you're on JAX or TensorFlow, for example. And it's really powerful. A lot of big companies have used keras for fast prototyping. Um, so module imports, this is a very vanilla kind of basic notebook. So, I mean, it only depends on TensorFlow, pandas, and it imports some metrics from sklearn, scikit-learn. So if you start the notebook, there's really not too much required for developing your environment. There's no crazy CUDA installations or anything here. Also, let me actually share this. I realize I don't have the link shared with the. What's the best way to do this, Sebastian? Should I add this
Uh,
to the chat?
yeah, put it in the chat, and if you can share it with me afterwards, we're gonna make it available to all the participants. But for now, as it's only a couple of participants, we can share it on the chat.
Okay, got it. Okay, so there's a link. Sweet, I'll give you guys some time. Some basics, we're using TensorFlow 2, and we're going to be using the MNIST dataset. So I guess I'll pause there if people want to open this up and check it out first. Maybe if you want to give me a thumbs up in like a minute or so, if each person can add a reaction, I'll move on once I think it's enough time for people to use it. I see a thumbs up from Joseph. Thumbs up from Sebastian. Talal, I hope I said that right. Elham. Okay, so it's about half. Daniel. Okay, so Tomi, Sahithi, Delaram. Um, okay, so I think I can move on. So we're gonna start with the MNIST data set. This is a really simple kind of like a hello world data set for image classification. A lot of people use the MNIST data set to show off the very beginning of machine learning and computer vision. So some of the early models would just be linear classifiers, k-nearest neighbors, random forests. SVMs were really popular, and then finally CNNs. So the topic of this talk is going to focus just on developing an early CNN. So it's going to have a very simple architecture. And then later on, we're going to add in convolutional layers and some max pooling layers and improve the performance by a few percent. This task is pretty easy to get high percentage in terms of classification. Most of the approaches here can get 90% or more, 95% or more. Doesn't take a lot of work, especially with the CNN. And so first, to get this data set, we're going to access the data set by calling it from the keras API. So keras has a datasets module, and that has an MNIST member variable that you can call and instantiate that way. A little bit about the data set. The images are 28 by 28 pixels. They're really small images. They're going to be binary, so there's no RGB data. It's just either 0 or 1. It's going to be grayscale, so 0 to 1. There's 60K training set images and labels and 10K test set images and labels. So first thing we do is we can instantiate MNIST on this cell. And then we can create our training set and testing set And each set, the split is going to be split up into the input and then the target variables. You can take a look at the data set sizes. The shapes here are a little unintuitive if you haven't seen it. It's kind of strange to see the shape just be an empty tuple. But this is just saying that the value of Y train is just a single integer or a single element. So I can keep moving. I'll show you an example of a single data point in X train. This is going to be an image. Here you can see we're getting an ND array. This is a NumPy multiple dimensional array. In our case, it's 2-dimensional with 28 rows, and each row is going to contain a vector of 28 items. These items are going to be within the range of 0 to 255 inclusive. And we can see that each of these pixels is going to represent the intensity of a single pixel in the handwritten image. I can go ahead and actually let's move on a little bit. I'll show you how to visualize these in a second. We can see the type here is NumPy ND array. So if you're not familiar with NumPy, we don't really need to use too much NumPy here. Our main data types that we're going to use are just ND array, and you can think of this as kind of like a Python list of lists. And in addition to having the array represented, we can also represent each value as a data type that maps nicely to C or C++. Because remember, this is all GPU stuff, so you have to care about unsigned ints or positive negative values, and it's going to need to kind of have some signed implementation, even though Python is meant to kind of be more dynamically typed than typed. So that's really the only detail about NumPy. Okay, cool. So one thing we can do, something that I think is useful to do too, anytime you're working with a new data set, is you can just try to test out a couple of the inputs. So something simple is we can actually take the input image that's 28 by 28. We can flatten it. So now it's just a single dimensional vector of 28 times 28. And then we can get the minimum value and the maximum value. And so this is just a little check to make sure our data is what we expect it to be. So the minimum value is 0, the maximum value is 255. And one thing that we can do too is it's nice to visualize your data and kind of get familiar with how it looks. So a really common library for data visualization in Python is a matplotlib. And we can just show one of the images with the default color palette. You can see here that it's going to have kind of like this dark navy blue and kind of like green and yellow color patterns. So one thing that people should be aware of too is, are you faithfully representing the data set in a way that makes sense to the domain? So in our case, our domain is handwritten digits, and nobody's writing on black paper with like a yellow Sharpie. So we want to kind of update this to show it in a way that makes more sense. So one thing that we see before this is that there's no RGB. It's just a single integer value, 0 to 255. And so if you want to map this to RGB, one function that we have inside of matplotlib is called a color palette. So a color palette is essentially a dictionary. It's like a lookup table. You can pass a single integer value and have it mapped to a RGB value. In this case, we have RGBA. A is alpha. Alpha is like how opaque. So if I'll explain that, it's kind of like the percent that you can show an image on screen. So in our case, we don't care about opacity. Everything is going to be fully opaque. So the value is set to 1. And then our mapping is going to be if our value from our MNIST data set is 0, that gets mapped to RGB all being equal to 1. Or if our value is set to 1 in our MNIST data set, then we map to all zeros. So we can show an example of that. And then we can specify the new color palette so that our data is actually represented correctly. We can see it's going to give us light gray, black, depending on, I guess, how hard people are pressing on the pen or the pencil when they created the data set. This is kind of a fun one. It's just like fun for people to look at. There's some other funny color palettes that you can check out. So, just for people to kind of know that that's there. Okay, cool. So that's the X-train data set. It's just a bunch of images, 28 by 28. The Y-train data set is going to be our target variable. So in this case, these handwritten digits, this is going to be the number 5 and the corresponding index of this image. And the Y-train data set is going to give us the value integer 5 for the class. That pretty much covers it. There's not too much to this data set. So I just wanted to move into some basic data set analysis. So obviously, the more complicated the data set, the more time you might want to spend here looking into the stats. One useful library is called Pandas. It lets you visualize data as a really useful data type. It's kind of analogous to, I think, like a database table. You can give it indexes. You can perform operations that are very similar to SQL operations. And so if we look at our input type, we know this is an ND array. We know that the shape is 60,000 and each value in that 60,000 is an unsigned int. And each of those values is going to correspond to a class. So one thing that we might want to check is, let's take a look at what our class imbalance looks like. So how many instances of data points do we have for each one of these classes? This is an important step to any sort of data analysis, because if you're dealing with an imbalanced class, you're going to have to take some precautions during training. There's several approaches that you can take. In our case, the class imbalance isn't too bad. We can see that the data point, the classes for the value 1 is about 6,700, and it's kind of like a smooth descent. Not too bad. This is, I think, pretty well behaved data set. And then at the very minimum, our class for the number 5 is about 54. So between the highest frequent or the most frequent data, the most frequent class and the least frequent class, it's not that big of a spread. However, I added some techniques that people can try in the class. If you want to improve upon your initial model, you can revisit your data set and you can do something like sampling. So you can downsample all the classes. For example, instead of taking 6,700, 6,200, 6,100, you might want to just take 5,400 from each of the top classes. That way you're making sure that they're all represented an equal amount of times in your data set. You could also oversample class number 5. There's also something called mini batches. Create a lot more train test splits and experiment with like stratifying your data set. But I kind of leave this to the audience. I figure that's a fun follow-up for people to kind of Google and do on their own. For our data set, it doesn't make too big of a difference. So I'll move to data processing. So starting with our X train and X test, what we can do is notice that since we're starting with our data in the range of 0 to 255, it's really difficult to push information through a neural network and maintain these values in a nice range like this. So without getting into too much details, so the most common input to most networks is going to be in the 0 to 1 range. This is kind of more for numerical stability. You don't want to explode your gradient. The more and more you apply these activation functions to these vectors, these 0 to 1 range, it can blow up and get to infinity pretty quickly, especially for the larger models. Similarly, if you have numbers that are very close to 0, it can also vanish completely, and you no longer have information to push to the network. So for us, if we start with 0 to 255, that's really bad. It makes it much more difficult. So a pretty well established standard is to just normalize right away to the 0 to 1 range. So what we can do is, typically in vanilla Python, you might do something like subtract the minimum and then divide by the I guess the height of the data, like the max minus the minimum. And that way you can apply this to all data points and get values between 0 and 1. But in keras, it's a really nice high-level programming API. So all you need to do is call the normalize function on the data set, and just be careful about the axis, because in our case, we have training and test, and this axis is going to need to be set to 1 so that you're applying it to the actual images themselves. Let's see. Okay, I didn't skip any cells. So I'll go ahead and run these and show you guys the difference. So before this, remember this image was ND array, and the values were between 0 and 255. Now they've been normalized. So that's good. That'll behave well when we pass it to the model. And then we can regraph it, and we can see that the intensity of the pixels has changed, which is expected. So that's good. And if we do the same thing, minimum and maximum, this is kind of just a sanity check at this point. So now we know that it is normalized. Like we don't have any outliers or something weird didn't happen where we still have a value that's outside of the 0 to 1 range. And so at this point, we're pretty much prepped the data set. There's some more advanced image processing that you can apply to these images. I don't want to get too into that because we're going to run out of time if we start applying like binarization and other things like different filters. But there's probably a ton of resources that have been covered at this point. If you want to do that, you can try to do that and get probably 1% better on the data set. And in the real world, you'll definitely want to do that. But for MNIST, it's okay to kind of skip it. So at this point, we can jump into some of the deep learning concepts. Just a simple neural network review. So neural networks, most commonly, a neural network is going to be a series of layers. Each layer is going to contain neurons. And these neurons themselves are going to have activation functions defined. So at the beginning, you're going to push in kind of like an input image or vector. It depends what your model is going to be classifying, but the information is going to get passed from the first layer through the intermediate layers and then finally to the output layer. And the signal to each input is going to be a number or a linear combination of the outputs from the previous neurons in the previous layers. The functions that you can apply, at this point, there's a lot of different activation functions. I'll skip ahead. I'll show you some slides and show you some common activation functions here. Some of the most common ones, let's see if I have my drawing tool, would be, I think, the logistic softmax, tangent H, or I forgot what that one's called, hyperbolic tangent, and then ReLU. These are the most common ones I think that are used. And the reason for this is it's due to the way that we can define the equation, the forward pass and the backwards pass, in terms of the same function or something easy to compute. So you'll notice here that for the logistic function, it's 1 over 1 plus e to the negative x. And if we take the derivative of the logistic function, we can actually get the value by taking the original value of the logistic function and multiplying it by 1 minus that original value. So if you essentially compute the value of this function on the forward pass, then when you compute it on the backwards pass, you can just use the stored value from when you previously calculated it. Similarly with this function as well, you just have to square it and then subtract it from 1. And then the rectified linear unit is basically just a piecewise rule-based function. So it's easy to calculate forwards and backwards either way. So, okay, let me clear this out. Okay, I think I lost my, there we go. Clear drawings. Okay, sorry guys. Okay, cool. So those would be some of the common activation functions. The behavior of the network is going to depend on those activation functions, the weights inside of the layers that connect the different layers and the different nodes to each other. And in order to train this network, I think, Sebastian, you said that everybody's familiar with backpropagation and training.
Yes.
Okay, so I don't have okay, so I won't go through this too much. So in order to implement our model, we're just going to start with something very simple. We're going to use the keras sequential function. This is going to start our computation graph as kind of like an empty list of layers and functions that are going to be applied in order. So to start, we can create a simple empty model. And then if we think of this as a computation graph, the first step that we want to do is just do a data operation. Our MNIST images are going to be 28 by 28, but we want to convert these into a flat list before passing it to the model. So we'll have a single dimensional vector that's size 28 times 28. And in vanilla Python, you can do this by calling numpy.flatten on the input. But since keras is really friendly, and this is a really common operation, especially if you have densely connected layers in a lot of the different models that you're going to encounter, this is actually given to us as a layer operation. So we can actually just pass our 28 by 28 image into a layer, and this layer is going to give us our flat one-dimensional vector. So we'll go ahead and add that one. The next thing we want to do is just add some densely connected layers. In our case, this is a very vanilla simple model, and I left a better model later on in this notebook, but for now we'll just start with this one. So this model is just going to have 128 units. Our activation function is going to be a ReLU, or a rectified linear unit, which is basically just the maximum of 0 and x, our input, which I just showed you on that slide 55. So you'll have that for reference too. And we'll run that cell. And then now for the last layer, what we want to do is add a softmax layer. The number of nodes in this layer is going to correspond to the number of classes that we have in our data set. In this case, we have 10 nodes for our 10 classes, 0 through 9. Softmax layer, again, is just defined as 1 over 1 plus e to the x. And the reason why it's nice, it has a range of 0 to 1, not inclusive. It doesn't include 0, doesn't include 1. It's smooth, it's differentiable, continuous. The derivative is defined. Oops, I think it's asking me if I was still in the notebook. Okay, hope that was okay. Yeah, we're good. The derivative is defined in terms of itself. And then we have our reference here. So we'll go ahead, add that one at the end. There's some info on backprop. I'll leave that to you guys if you want to go more in depth. It represents how you can think of the function graph as the forward pass and backward pass and use chain rule. So I went over this. There's probably a link to one of the talks I did that talks more about this in detail, but the slides are there for reference. Now, the last thing that we can do too is we need to consider how training works. So in our case, our data set is giving us integers that correspond to the class number, but our softmax layer is going to give us a vector that's 10 dimensions, and we need to create a optimization that we have some sort of a loss function that learns how to train this model to give us output similar to our class prediction. So what's really common for training simple neural networks when you have a softmax layer is to use this type of loss. It's more generally in the theory, it's mutual information between two random variables. But this is also in like, I guess in neural network architecture terms, this is like a categorical cross entropy. It's categorical because you can take a single number 4 and you can map that into a one-hot encoded vector. So in this case, we'll get the value in the corresponding index of this vector being 1, and all the other values are going to be 0. So it basically says the corresponding index of 4 is going to be index 0, 1, 2, 3, 4, add a 1 there. And then our neural network, since it's got that softmax layer at the end, we're going to have probably an output similar to this, where all of the values are going to be either close to 0 or close to 1. And these two vectors are training optimization. Our loss is going to learn how to maximize the mutual information between our one hot encoded vector, our ground truth value, and our model's predicted softmax layer output. There's some cool reading about this. It's related to like information theory. I left that as a link, mutual information, but that's kind of how this works. It does a lot under the hood, and there's a lot of theory behind it that explains how it works. But that's really all you need to know. It's just maximizing the similarity of our one hot encoded vector to our softmax output. We also have an optimizer that tells us how to run back propagation. Atom is a really nice one because it takes into account the derivative and second derivative. So in your gradient surface, you can get kind of like a concept of the speed that you're descending towards the minimum. Um, and Atom is a really cool algorithm because it's able to find the local minimums really quickly and then kind of navigate on that surface in a smart way. Um, yeah, without getting too into the details. So when we're running training too, we also have the option to pass in some metrics. So while we're watching our model train, we have some sort of output that tells us a little bit more about the health of the training. So for example, we can watch the accuracy change as we train from epoch to epoch. And you can read more about some of the metrics that you have in keras and experiment with those. There's a lot of interesting stuff you can add here that you can log. But in our case, we'll just make it simple and run 3 epochs, and we're only going to watch the loss and the accuracy. So this should take about a minute. We can also see the model summary after this. Model summary, model dot summary. This tells you about the architecture of your model. Also, sorry if my voice is a little raspy. I'm getting killed by allergies this year. Okay, cool. So you can see in the first epoch, our loss starts at about 27%, and then it slowly decreases. We can even run it for more epochs. But with just this simple model, we only have 2 densely connected layers and a softmax, and we're able to get 97, almost 98% on MNIST. So this is really good. We can also see the shapes and the inputs and outputs of all these different layers. So our original flatten, it's going to be 28 by 28, which is 784. And then we have our layers of 128. So very simple model and surprisingly good accuracy. So that's kind of like our basic hello world. Now we can run the evaluation and call it with dot evaluate, and we pass in our evaluation set or test set and take the input and then our target variables. And this is going to give us our validation loss and our validation accuracy. And I actually don't think I plotted these. So we'll do val loss. Yeah. So again, yeah, 97% performance. So we got a really good score on the training set, but it's not always the case that the model that you've trained on your training set generalizes to data that it hasn't seen before. In this case, MNIST is very simple, so the digits don't have a lot of variation between them, between the training set and the validation set. So training a model on the training set will give you usually a pretty good score on your validation set. It won't really overfit too much. In the real world, it's something you need to be careful about. And going back to our training, when we have our metrics on accuracy, there's ways for you to actually calculate accuracy during training for images that your model hasn't seen yet. That way you can see whether or not your model is overfitting, and you can stop training at that point instead of potentially training for a whole nother day and paying, like $8 an hour for your expensive EC2 instance. So that's good to make sure that you have like good logging. And keras it's a simple save and load API, so you can just save and load it as MNIST model 1. We can also run inference using .predict. The only caveat is this needs to be wrapped in a list. And now we can visualize the output. So this will show us the softmax layers that I was telling you guys about earlier. Another thing to note too, if you're ever dealing with GPUs and training, sometimes these data types will give you an issue. If you're trying to multiply like an unsigned integer 8 with a float 32, it might complain. So that's why I thought it would be worth mentioning, and kind of that step that I talked about earlier with the ND arrays and the unsigned int 8. Here you can see there's your 10-dimensional vector. It uses scientific notation, which is, I think, kind of annoying to most of us. But this is essentially saying it's this number multiplied by 10 to the negative 8. So the larger the exponent, the smaller or the more decimal places away from zero. So all of these are going to be really small numbers. And then you can see here, this number, e to the -1, this is only moving the decimal place one digit to the left. So this is basically 0.9998. And in order to figure out what index this value corresponds to, we can use np.argmax, which is asking the question, which index of this, which index contains the largest value in this array? And that index is 7. And we can check that this is predicted correctly, graph our original input, and it is in fact the 7, so it's good. We'll jump to convolutional neural networks now, so we can move away from a very simple like vanilla two-layer model. We can add some convolutions and some max pooling. I think maybe it can move a little faster through this, save some time for questions. Essentially, convolutions and max pooling, I'll use my slides as reference again. So you can think of convolutions as taking a input image, it's my little drawing tool, and then applying a filter or a mask. And you can think of this mask having like corresponding indexes on the input image and also the filter. And what you'll do is you'll multiply the corresponding index. We'll call this like I sub j, and then this is our filter f. And then you multiply by f I sub j. And you'll do this for all I and for all j. So in this case, it's just 1, 2, 3, and 1, 2, 3. So it'll be 9 times 0 plus 4 times 2 plus 1 times 4. Oh, interesting. 1 times 4 and 1 times 1. I think the order is a little messed up, but you get the point. Oh, I stopped sharing. And once you have the sum of all of these corresponding indexes, you can get the final value 16. And then what you want to do is take your mask and move it one more to the right or left or down. So in this case, we'll slide it to the next position and then the next position. And then we'll move it down one and multiply it across these. And so the number of potential places you can slide across to the right or down will tell us the dimensionality of our output array. Sorry, I noticed there's some questions. Should I stop right now and take some questions?
No,
Feel free to
it's
unmute.
just me texting on the chat saying that they can unmute or put their questions on the chat.
Okay, got you. Cool. So hopefully that's pretty straightforward example of a convolution being applied. We can take the same concept of applying this window to a subset of the input image, and we can generalize that to max pooling. So for the max pooling operation, instead of multiplying element-wise and then taking the sum, we can just consider the input, the subset of our input, and it's straightforward naming max pooling. We'll find the maximum value of this set. So our values to consider are going to be everything inside of this kind of like pinkish purple. And our maximum value is going to be +3. So then we get our value 3. Same thing with, let's take yellow, for example. All the values we have 0, 1, and 5. So 5 will be the largest value. Min pooling, same thing, and then average pooling will just take the mean of this. If you convert this into a flat list, the one-dimensional vector, and take the mean, then you have average pooling. So those are some other common operations worth mentioning. In our case, we're going to use convolution and max pooling. So, okay. So I won't go through this too much just to save time. Another thing that we need to do too is we need to expand the dimensions of our data set in order to pass it into this model. So previously we were working with a vector that was 60K and each element was 28 by 28. When we expand the dimensions, we add another. So instead of a 2D image, now we have a 3D image, and each value is just going to be like um, a single 0, 1, or in the range of 0, 1. So we can create our same model. We're going to call it CNN model this time. And we're going to use the same keras sequential API. And we're going to actually create a couple pairs. So we're going to pair a conv 2D layer with a max pooling 2D layer, and then create another pair here. And then we'll run that same flatten function that we did the first time around. And then we'll add dropout. I'll add dropout, an explanation of dropout up here. I forgot to add that. Dropout essentially, it lets you lose some information along the way so that your model is only trying to remember the important features, and it kind of makes the model learn stuff that's more favored for classification. After dropout, we're going to add another dense layer with a softmax, the same way we can get the output from the first model. Go ahead and run this. And here's our model summary. You could also note the total number of params is really going to blow up compared to original models. So we have 38 or 30, almost 35,000 parameters, whereas the original model, oh, it had 118. Okay, my bad. So we actually have less parameters because we no longer have the densely connected layers. So that's actually a benefit. So we can actually get a stronger model. I forgot, I was thinking that this was a convolutional network with less convolutions, but the densely connected layers, it means you have to multiply across all these filters and then across each of these nodes. So this ends up being a larger model, even though it's not as performant. By just adding some convolutional layers, you can cut the model size by a large factor, like a factor of maybe 4, and get a better performing model overall. We'll do the same thing. We can compile the model with the same optimizer and loss and accuracy metric. And then I'll run this one for a little bit longer and I'll take some questions. Feel free to write some stuff in the chat. I can revisit stuff right now because this will probably take about 2 minutes. So, or if you want to get some coffee.
Maybe I can start with one question. So what is for you the main advantage of using keras? Why using keras instead of another framework?
I like keras because essentially when you're doing any sort of data processing or you're defining some common operations, or even when you're working on your definition of training and evaluation, sometimes it takes a lot of effort to tell your model exactly how to read in data points and transform them to be used in the actual model, like in the expected format and input. And so after so many years of engineers kind of writing out all these very tedious steps to get from point A to point B with like data transforms or with like model training formulas, keras is basically saying, okay, we can actually put an entire API on top of that, and you can create your entire training loop. Like you can instantiate your training parameters just in one function call, and then you can just do a dot fit on your data. So, you know, for me, for example, when I'm working with my job and I'm using PyTorch, this might end up expanding into like 300-400 lines of code where you're doing your own PyTorch data loader. You're telling the model, you know, in certain conditions, you have to multiply and do this or apply that. So it's really nice for prototyping. It's like very high level. So if you just want to test stuff, it's kind of like it sounds funny to say, but it's almost like if you consider all of these different libraries like TensorFlow and PyTorch, it's like making them more Pythonic, even though they're already in Python. It makes it more simple.
Makes a lot of sense. Thank you. And yeah, if you guys remember from the PyTorch tutorial, there were much more lines of code than what we're seeing here. Like it's really easy. You don't have to write your training loop and everything. It's already there. So now my follow-up question for you, Hunter, is what is the disadvantage compared to PyTorch?
Yeah, so you can't do as much stuff. It's like the same downfalls when you talk about Python and C++. Um, you don't have as much fine-grained control. So if you want to do very specific things or try to optimize stuff a little bit more, um, excuse me. For example, with us, sometimes when we're doing our data sets, we have multiple steps of transforms. So I might take an image that's paired with a corresponding JSON file that has some information about the image. Um, and we might have to somehow take these two data inputs and create some transformation on top of them. And each of those transformations might take a certain amount of time. So at each point in that process, you might want to cache or save it to disk. And these more complicated data pipelines, it's not as easy to deal with that in keras. It's much easier to kind of write something ad hoc and do like a more complicated data loader in PyTorch. Um, but it gives you more flexibility with how you're moving your data around. Um, Similarly with the types of models that you're using, if you're trying to like chase performance, um, a lot of the times you'll be checking a website kind of like papers with code, and you'll be looking at the leaderboards for some task, like let's say image classification as a task. You might say, okay, cool, like it looks like this new model just came out this last year. I'm going to go into the repo and try to adapt it to my data set. And you're going to need to get into the weeds of the PyTorch or the TensorFlow to kind of adapt it to your own use case. Because these things are going to be trained on things like ImageNet, but in your case, your data set's going to be different. Okay, we got a question. What exactly does the number indicate in the dropout? I actually don't know. I forget. So let's check. You can actually do the good old question mark syntax. Okay, cool. So applies a dropout to the input, sets input units to 0 with a frequency of rate. So in our case, rate is going to be 0.5 at each step during training time, which helps prevent overfitting. Fraction of the input units to drop. Yeah. So this means we'll drop 50% of the input units. That's also a good point to bring up. If you're never sure, or if you're not sure of something, um, most of the times these libraries inside of the actual GitHub repo, it'll provide a doc string. So if we go to keras GitHub, I'll do like a little aside right now. And then I'll command K and I'll search for dropout. Maybe this will show it, maybe not. Um, we can just click on any of these. I think, okay, let's click on this one. So a lot of these will have this doc string. This is defined in the source code. And if you're not sure about the input, like maybe you want to know about what the function calls do, what the expected output is, you can just take that value the full path from the top level of the module all the way down to the function name and put a question mark next to it, and it'll print out that doc string. So then you have some examples and some information about input, output, and data types. Cool. So we can move to our new model. We just ran cnn.fit 5 epochs, and we can save the output of this in history. So we can see that we have even better performance. We've bumped it up to 98% on the training set. We can check the validation. Looks like it responded well. It's about 98%. And this is from a previous run, but it's nearly the same. So you can see in the first model, we got about 96%. And then in our final model, we got 98%, 98.5%. So it's a 2% improvement in performance with about a 3 to 4 times smaller model in terms of trainable parameters. I wanted to add this step in here too, so we can actually show what's happening under the hood. So remember when we defined all of those convolutions and max pooling layers? Each of those values in our mask in the filter was a trainable parameter itself. So if we go back to here, if we go back to here in this filter, each one of these values is instantiated to just like random noise. And then when you train the algorithm, it learns what type of filter or mask is extracting features most effectively for optimizing the objective. So we can loop through all the layers in the model, and we can see we have our conv2D, our max pooling, our second conv2D, second max pooling. Then we have that flatten, the dropout, and then the final softmax layer. So if you actually want to take a look at what these layers look like, I think this is kind of cool because it illustrates what's happening under the hood. We can grab the weights from this. The weights are given to you as a tuple, so the 0th element and the first element. The first element is going to be the filter itself, and then the second element are going to be the biases in the model. So we can see here that the filter is a 3x3. There's let's see, there's one filter and there's 32 channels, and we have 32 biases. Now the second layer is a little bit more complicated because it's kind of dependent on the layer before it. So in our case, because we have 32 filters or 32 channels for this first filter, when we apply the next filter, now we have 32 filters, and then each of those has like 64 channels. So it gets it becomes a much wider model the deeper you get when you're applying convolutions. We can actually see what this convolutional this learned filter looks like. In our case, it's just going to be between -1 to +1, and we can even visualize it. So this is a pretty silly like type of thing to visualize. It's more useful when you're getting into bigger models, but when you get into like mask RC, then maybe this has something useful. Let's do this. Okay, this is a little bit better. So the deeper you get in these models, sorry, I should have had an example here. This one's okay. This could be a better graphic, but actually, let's do this. I think this is a okay. This would be an example of the intermediate filters that have been learned. So you can see here in the very first layer, in the very first layers of the network at least, It's just going to learn, that's my annotation. It's just going to learn kind of like concepts where you have changes in intensity. These can either be lines or curves or kind of like different shapes. And then if you imagine applying each one of these to the original image in that sliding window, and you take the linear combination of all of these and maybe apply like some max pooling or something, then you can get more intermediate features where several of these applied with a different weight can maybe get you the shape of a nose or maybe get you the shape of an eye. And then you put all of these together and then you can get the shapes of faces. So that's kind of what I wanted to demonstrate here. But for MNIST, it's not really very easy to see when you're working with just like a 3x3 filter. But I did include it in this tutorial because you can definitely do this with bigger models and get more interesting results. So if you want to graph all of them, you can go through and see what our 32 learned filters look like. I know, very interesting. And so you can even check what applying these filters to the input image looks like. This is a little bit more interesting. So we can create a new model. We can tell it to take the original model's inputs and then use the outputs at that first convolutional layer. So you're not going to run the full first layer to softmax. You're just going to run from the first layer to the output of that first convolutional layer. And then we can get a single image from our training set. We'll show the original image. And then we have to set up the dimensions to pass to the model. So expand dims, axis is 0. And then you can do dot predict and get the feature maps. And here you can see the shape. So this is going to match up with the original model summary. If you go back up, you can see model summary here, 26, 26, 32. And then our output 26, 26, 32. And so we have filters of size 26 by 26 with 32 channels. We can show this, and this is the cool one because this is actually showing you what each of those 3x3 like boring filters does to your input image. So by learning a set of features, it can take some new information from each of these applications of the filter and pass it down the network. Again, simple MNIST, not too crazy to look at, but it's definitely worthwhile if you're trying to debug and look at bigger, more interesting models. So earlier we saved that value history. This is going to give us the value of the accuracy and the losses from training. So something you can do with keras is you can use TensorBoard, which is going to give you a graph like this, but it's going to give you like live updates. In our case, we can just visualize it afterwards. There's not really a danger of overfitting, but if there is, you do want to use that live updating TensorBoard. In our case, we can just see the performance across 4 epochs. We can see that the accuracy, it continues to increase. It gets pretty high up to 98. Probably could go to 99 if you trained longer. And similarly with the model loss, it approaches 0 pretty quickly. Now what we can do is we can visualize some of the model predictions. So we have our model. We can do predict, and we can get those softmax 10-dimensional vectors. Then we need to get the maximum index, or the index of the maximum value with argmax. And this will give us our predicted classes. So if we go up here, you can see, oops. Predicted classes, we have our values like 7. Y-test is the same. If you look at y-test, it's just giving us integers. So then you can use this NumPy syntax and just check to get all the indices that match up. So you can do a correct indices and incorrect indices and get your correct predictions and incorrect predictions. And this is just hard-coded. Like we know that we have 9 separate classes. So we can just give some examples like this. So we can get 9 total correctly predicted numbers. So predicted 7, class 7. We can also get some examples of some difficult cases. So this six is it's incorrectly predicted. It looks kind of like a zero. This number nine looks like a seven, or yeah, this one it's a two, but it looks like a seven. So maybe you can actually get better performance if you change the sizes of your kernels for your softmax function. I mean, sorry, your convolutional functions. Instead of 3 by 3, maybe you can do 4 by 4 or something like that. Um, Nonetheless, we still have really good performance, so it's hard to beat like 98%. And finally, we can get to plotting some metrics. So sklearn is a great library for giving us some information about our model performance. I like to use confusion matrix and classification report. Whenever we do proof of concepts, these are the two that we throw around with our group of coworkers in the technical panels the most. A confusion matrix, if you haven't seen it before, it's a, a, a 2D array with two axes. One is going to give you the true label, one is going to give you the predicted label. And you can get a correlation and you can see the total number of correctly predicted. And then if it's predicted incorrectly, you can see exactly what class it was confused with. So in our case, you can see our true label. If it's 0, we predict 978 0 data points correctly, but we predict one of those as a 7, and we predict another one of those as an 8. So that's kind of how you can interpret it. Similarly with 6, we predict some 6s as 0s. Some of them as 2 of them as 1, one of them as 2, so on and so forth. So what's good about this is, let's say that this was predicted as 100. This can actually tell us a lot about the difficulties that we're having with our model and influence the next decisions we make and how to optimize. So for example, if we have a lot of trouble with this 6 class, we might revisit the data set and include more examples of 6. Another thing too is classification report. So you can get precision and recall. Precision and recall, are people familiar with precision and recall? Let's see.
It should be.
Okay, so I won't really explain that. But here it's I mean, all of them are basically 99. So but this is basically telling you, out of all of those predicted, how many of them are actually true for precision or for recall. You know, you can define recall as out of all of them that exist, how many of those were predicted. Yeah, so I'll stop there. I think that's about time, right? And take some questions.
Thank you so much, Hunter. That was great. So now we have some time for questions if you guys have some. So feel free to directly unmute or ask your question. So there is a question by Daniel, not quite as related to this workshop in particular, but I'm curious about what kinds of tasks you use computer vision for in construction.
Oh yeah, okay, this is cool. So let's show you some cool stuff for Procore. So we can have a construction floor plan. Okay, sweet. So a common job in construction is actually called estimating. And so as an estimator, something that you might do is you have to look at these PDFs of floor plans all day and figure out the scope of the project. So scope of the project is kind of defined by materials and also by how much work it's going to take to install or build those materials the right way. So we can divide those into 3 categories, like concrete for the foundation, or square foot of rooms, square foot of roof, and then also like linear feet of wall. So in our case, what's useful for us to do is we can make the estimator's job a lot easier, and we can do something called semantic segmentation, which is finding the polygon outlines that represent each of these rooms. And if we can do that, let's say kind of like this, You can bear with me, I'll try to draw over all of the rooms. But if you imagine we can segment this perfectly, usually most drawings at the very bottom will have a legend, and it'll tell us the relationship between number of pixels in this image to real measurements like feet and inches. So if we have really accurate segmentations, we can actually estimate if this is like a rectangle, you can just do a height times width. And you can say this covered patio is actually like X amount of feet or square feet. And so that's one of our big projects right now is area takeoff. We're working on estimating for that. Um, Other cases for construction, image, or computer vision. Another one would be progress updates. So you could actually take images from phones, not just images that are coming from PDFs of floor plans. But there's a lot of cases where people have like security cameras on the job site, and you can track the work being done. So for example, if you're looking at the beginning of a project, one of the first things to do is to do something called grading, where you're moving all the dirt around, you're creating like a smooth building pad, or maybe you're creating ramps because you have an underground parking structure, something like that. So you're going to have these huge bulldozers on the job site, and you can actually track the movement of the bulldozers and estimate some sort of like progress tracking based on that. Or if you have people being unsafe on the job site, you can see if they're actually wearing hard hats or safety vests. So you can do like instance classification because you don't care too much about like the exact outline of people. You can just put a bounding box over them. So instead of semantic segmentation, it's instance segmentation. And then you can find the hard hats, safety vests, things like that. That one's kind of a new one. It's not something that we at Procore are spending a lot of time on right now, but there are some integrators that, as part of the Procore marketplace, you can actually buy like a membership to one of the integrators, and they'll do progress tracking with instance segmentation most of the time. Um, what are some other examples? There's also kind of like a new frontier where you're using like CAD drawings. So these are like 3D drawings. You can think about things like SolidWorks, and people are doing overlays where if you can take enough images of the job site from different perspectives, you can build a 3D model of your job site, real images, and you can somehow overlay your CAD model on top of that, and you can like peel back the layers of the CAD model and see what's being installed. That's um that's kind of like a more futuristic crazy implementation that's 3D imaging is pretty brand new for me, so I think that one's
Yeah, that sounds
probably the
really
most interesting to me.
intense.
Yeah, it's not stuff that I really work on. I'm mainly working on document processing, so I would be the person trying to pull information out of these floor plans.
Okay. Okay, that's really
Yeah,
cool. Well, thanks.
yeah, thanks.
Any other questions? Maybe I can ask one related to this workshop. So, from what I understood, keras would be more for prototyping, and if we want to do more complex stuff, we would be using like another framework, let's say PyTorch or like raw TensorFlow. What is the boundary? Like, at what point do we choose to move on to PyTorch for more complicating things? Because I know you can sort of use custom things as well for keras, like let's say custom loss function or a custom uh, like activation function. So let's say you're working for Procore and then you want to start a new project. At what point do you shift to a more complicated framework?
Um, yeah, so I think I'll try to split that one in two. So I'll answer the keras to TensorFlow or to PyTorch, kind of like the sliding scale first. Um, so I think it depends on how familiar you are with different model architectures. For example, like if I go ahead and share screen, we can go to the let's go to the MNIST Wikipedia. So if you're using keras, something you can check back here is you can actually look at the performance of different model architectures. So if this is familiar to you, you might have a 2-layer network where one layer has 784, the next layer has 800. Or, you might get into more complicated stuff like this, 13 layers, and then, now you start counting up and trying to match up dimensions, and it could get a little tricky. But if you're familiar and you want to implement some of this stuff from scratch, I think Keras is a really nice API for doing so. But I think once you start getting into more like research or like, models that have come out in the last 5 years and they're experimenting with all these different, I'll show you mass star scanning. This is a pretty common. Once you start getting into stuff like this and it gets more and more complicated, I think at this point, you might want to transition into something like PyTorch or Tensorflow, because then you start to get a little bit more concerned with like library organization. So you can split up each one of these into modules, and it's pretty common that these are somehow represented in modules when you show architectural diagrams. So for example, all of this one color might be in one file, all of this yellow color might be saved in another file. And since you're getting into more of like an architecture implementation, you can move down one level and move into like PyTorch and TensorFlow. And you can start implementing your own classes. And then each of these somehow, when you start training things like this, you might need to do like some really some like unique connections between them and maybe pre-train some. So for example, this ResNet 50 backbone, this is going to be pre-trained on ResNet. The featured pyramid network might already have some weights you can load from some model library. And then when you're training all of these, this might need to be like closely related to your data set. So maybe your data loader gets a little complicated. So I think it's mainly related to like the complexity of your architecture. I think like from the TensorFlow, PyTorch versus Keras. And then to answer, oh, sorry.
Go ahead, go ahead.
Yeah, and then to kind of answer the question about like me specifically, I feel like I'm not really like a PyTorch or TensorFlow super user. I'm more like familiar with taking a repo, like I'll go into maybe like DeepLab or MaskRCNN or some other model architecture that exists. And I'll have to try to get that architecture and the training loop and the evaluation, all that stuff. I need to try to get it to work on our own data. So for us, I don't really go the path of implementing models from scratch. We've tried to implement some models from scratch based on like explanations and papers, but the delivery timeline for stuff like that, it's much more, it's a lot harder to estimate the time that it's going to take to get those models implemented, because there's issues that come up that you can't really anticipate. So typically, if you have a working model in a repo, and if you just know how to get your data set to look like the same schema as the data set that they're using, then you can start training right away and get good results right away. So we wouldn't typically implement things from scratch. We would more likely, like, let's say, I'll show an example. We'll go to like MaskRCNN GitHub. And I'll go to a GitHub like this and I'll say, okay, cool. Like we have MaskRCNN here. They're going to provide me like a demo notebook, some training. I might even have some model zoo that I can try. So like the backbones, I might have a backbone that gives me like 2 million parameters, or I might have a really large backbone that gives me like 10 million parameters. Or maybe if you're using GPT, it's like in the billions of parameters, and you can just basically test out each one of those different combinations of backbones and like maybe even loss functions on your own data sets. And you'll do like a comprehensive search and see what works best. And then once you decide on one of those best combinations of the model architecture, then you can like more work on fine tuning. Sorry, it's a little drawn out, but I want to make sure I explain that the right way.
No, that was perfect. Thank you so much, Hunter. I'm gonna stop the